Hi everyone, hope you're doing well. This video is going to continue on our lesson on solubility. It is on 8.5 and it is going to assume that you've had plenty of time to familiarize yourself with the idea of the properties of water and why something dissolves, why something is maybe dilute versus concentrated, and if you have dissolved as much solute into the solvent as possible, why do we call something saturated? Okay, so we are going to go back to this term and we're going to introduce a couple of other things when as opposed to saturated, when something is unsaturated, which I think you can guess, and when something is super saturated. To have a better understanding of what these terms are and to better use them in your daily scientific vocabulary, I'm going to ask you to take a look at page 392 in the textbook, so you can pause the video now, and look at the table, labeled table 1. It says solubility of common solutes in water at 20 degrees Celsius. Okay. Solubility, anytime we discuss solubility, it is almost always connected or spoken in reference to a specific temperature. Why? Well, to actually answer that question and to have a better understanding of these three definitions, we're going to have to explore a little bit more about what it means to actually be dissolved. What does it mean for an ionic compound to dissolve? Okay. 8.3 talks about dissociation very well. So if this video is not clear enough, please go back to chapter 8.3 and read it. Okay, so let's pretend this is a beaker of water. And of course, with the naked eye, we have a jump between two different mediums. We have water on one side, and we have air on the other side. That's as far as our eyeballs can see. But if we were to take some kind of magical microscope that lets us see not even, cells, but like goes deeper and actually lets us see atoms and compounds and molecules, like visually, we would see that it's not just a single body of a fluid. It's actually individual water molecules that are chaotically moving around everywhere. Okay, and even if a body of water looks like it is completely still, the molecules are constantly moving. That would be the solvent portion. So where's a solute? Well, there it is. There it is. There it is. There it is. They are also moving, of course. They are also moving around, but they are constantly being surrounded by this chaotic current of water molecules moving around and surrounding in the first place. So in essence, every single thing, the solutes, the solvents, they are all sort of moving around together. It's not a perfect analogy, but another way we can sort of add to this picture is that as the water molecules move, okay, you can sort of guess that there is actually, if there's a water molecule, and here's another water molecule, and it's moving this way, and it's moving this way, there is, I know I drew these arrows, but there is space between these water molecules. Here's another water molecule. And yes, they may be really close together, but it doesn't mean that they are connected to each other. They're not bonded. So technically, we can argue that there is space between water molecules. And guess what fills that space? You guessed it. A solute. A solute. Solute. So we are adding to the analogy that we had, or adding to the idea of how we have a cation or an anion, and it is surrounded by water molecules, right? So that's the one way we sort of talked about how cations and anions, so solutes, are sort of dissolved in water. This area, where's my eraser? This area is what I'm talking about. Water molecules have space between them, which allows ions to sort of reside inside. Okay, so, but you can imagine from there, we have a limited amount of water molecules, which means I have a limited amount of space. When all that space is filled up, we say that the solution is saturated. If not all the space is, if not all the space is filled up, like for example, let's pretend those locations, this part right here and that part right here was empty, well, then this solution is unsaturated. Confusion? Questions? Send me a message. But that is, I think, an easy way to discuss unsaturated versus saturated. These two definitions are a little bit more easier to digest. So what is supersaturated? To have a better understanding of that, I need to draw your attention to the next graph that is on page 393. Essentially, it's called figure 2. Right? There's a graph called figure 2. And in short, it is called a solubility graph. Oops, excuse me. And it does a pretty good job of explaining how solubility always has to be connected to temperature. So this is temperature in degrees Celsius. The graph isn't going to be the best, so I highly recommend you follow along with me through the textbook once again. Okay. And we have solubility as the y-axis, and that is a specific number of grams per 100 grams of water. Now, 100 grams of water, please note that the density of H2O is 1 gram per 1 milliliter. In other words, when I say 100 grams of water, it basically means inside 100 milliliters of water, how many grams of a solute is going to dissolve. This particular curve is talking about sucrose, okay? Which is basically table sugar, refined sugar. Okay, one of the worst things for you, highly addictive. Yeah, anyways. And then we have 100, we have 200, we have 300, and we have 400, and of course it goes so on and so forth. Okay. At approximately at 20 degrees Celsius, the solubility of sugar is 200 grams per 100 milliliters of water. Okay, and that's it. So do we say, okay, so solubility of sugar is 200 grams per 100 milliliters of water. But do you also notice that if the temperature decreases, the amount of sugar that is dissolved decreases, and if the temperature increases, you will see that the solubility of sugar also increases. Something like that. And why is that? Well, again, this doesn't have anything to do with supersaturation just yet. If the temperature increases, what happens to the, I guess, the kinetic energy, the speed in which the solvent is the speed in which the water molecules begin to move and vibrate, the speed in which they collide, the speed in which or the energy that they have as they collide, they move, they vibrate, they rotate, they spin, whatever the case may be. We can argue that if these water molecules are moving faster and more vigorously, then the space between the water molecules may increase. So before, the water molecules were sort of like that, and they were spinning, and they were spinning and moving, and there was this much space. Okay? So again, terrible, terrible analogy, but if it had more kinetic energy, as opposed to moving up to here, maybe it would travel further. And as opposed to moving just up to here, it would travel further. In essence, the space that is found between the water molecules will increase. And if the space increases, will there be more opportunity or more space for the solutes to dissolve, or the solutes to be uniformly distributed? Absolutely. In short, as a general rule, for solids, when temperature increases, then the solubility of a solute in solid form will also increase. Hope that makes sense. So if a glass of water was in room temperature or 20 degrees Celsius, the amount of sugar that we can dissolve is going to be 200 grams. If I boiled that water or heated that water up, you will find that you would be able to dissolve more. And in turn, this graph will give you approximately 300 grams per 100 milliliters of water. Okay? We can dissolve that much more, a difference of 100 grams, just because I heated it at 40 degrees. There is no mathematical equation that will show us how much each is going to dissolve. This is all based on observations. And there we can do a lot more, but hold off for a second. Let's explore this just a little bit more, just to make sure that we have a good understanding of it. So here's one question you can ask yourself. Question 1, okay? At 20 degrees Celsius, okay, if I pour 201 grams of water, of sugar in 100 milliliters of water, how much solid would remain? Pause the video, think very quickly. It's not a trick question. It's supposed to be a little simple. Going once, going twice. Example 2. I'm talking about the same solution here. If the solution was heated to 80, about 60 degrees Celsius, how much more sugar can be dissolved until saturation? Once and twice. Afterwards, the solution was cooled down to 0 degrees Celsius. And what happens? These are my 3 questions. So let's start with the first one. At 20 degrees Celsius, if I pour 201 grams of sugar in 100 milliliters of water, how much solid should remain? I'm jumping the gun here. Pause the video, answer all 3 questions if possible. I'm going to continue on, assuming you did pause the video. If I pour 201 grams of sugar inside 100 milliliters of water, well, just as a graph suggests, I can only hold about 200. In essence, approximately 1 gram of sugar would remain in solid form. There's no more space for it. So even if it wants to dissolve, it can. The real way of explaining it would be, or the correct way of explaining it would be, it can dissolve. Water will randomly choose to surround that last remaining gram of sugar. But in doing so, it will cause another gram of sugar that was already dissolved to be displaced and turn back into solid form. So I dissolve 1 gram, but I end up, I guess, crystallizing 1 gram. And so, in essence, it will always have 1 gram of sugar remaining in solid. If the solution was heated to 60 degrees Celsius, how much more sugar can be dissolved? Well, I can have 300 grams dissolved, And if I already dissolved 200, then there is quote unquote room for 99 grams of sugar, 99 more grams of sugar to be dissolved. Okay. So let's pretend we dissolve 300 grams. Exercise 3. Afterwards, if the solution was cooled down to 0 degrees Celsius, what happens? Well, right now, if we are at 60 degrees, how many grams of sugar are there? 300. At 0 degrees Celsius, if you look at the graph, it looks to be approximately 170 grams. If this was quickly cooled, the amount of sugar inside water would be 300 grams. The amount of space available is 170. When there is more solute dissolved than the maximum quantity possible, this is what we call super saturated. It is beyond the saturation point. So there's my definition of super saturated. Well, what happens? Nothing really. Immediately, so in the very beginning, or as soon as the volume of water is cooled down, you will still have 300 grams of sugar dissolved inside the cool glass of water. But if you give it time, slowly but surely, the difference of 330 grams of sugar is slowly going to crystallize out. Crystallize out. Okay? And this is where you may want to clarify your knowledge and get a little bit more detail by reading page 393. A very interesting application would be rock candy. Have you ever seen rock candy? You go to the ROM or any kind of museum that has a little confectionery, or you go to Sugar Mountain, you go to a candy store or whatever, you will find that there is a little wooden stick and it has these sugar crystals clumped all over it, right? Sometimes it's pink, sometimes it's blue, sometimes it's yellow, it's all flavored or whatever. Where's that coming from? Well, they actually use a very simple super saturation technique. They take water and then they boil it. And then they put lots and lots of sugar into it, okay? Turning you into more like that, okay? And so this becomes saturated with sugar. But once we saturate it with sugar at, let's say, 100 degrees Celsius, they will take that same solution and they will cool it down into a lower temperature. And as soon as that happens, what the heck? This becomes super saturated. The amount of sugar that they can hold, that the solution can hold at 100 degrees is so much more than what it can hold at 0 degrees. And so what happens? All that sugar that cannot be dissolved there, there's no space for it anymore. As the water molecules slow down, it will have to crystallize. That is when they come in, stick a bunch of wooden little handles into it, okay, with a little bit of sugar sort of dabbed onto the end as a way to crystallize, as a seed. And the super saturated solutions will, as it cools down, allow the sugars to crystallize and grow from this seed. Because as you might imagine, it's a lot easier for a compound to build on similar compounds as opposed to creating one on its own. That's it. So next time you see one of these rock candy things, go and enjoy, knowing that chemistry was involved in building it. Please go to your textbook and flip over to page 394. Take a very good look at the larger solubility curves of a variety of different ionic compounds and study it. Using that solubility curve graph, I'd like you to try studying the sample problem on the same page, on page 394. And then try practicing questions 1 to 3. This is going to be very important, so do not sort of skip by saying, I want to go to the chapter questions. Do these mid-section practice questions, okay? And when you are ready, tune into the next video.